Hey guys, welcome to day 27, and today we are going to be talking more about testing with our binary search trees. If you don't have the project and want to code along with me, I'll put the link down below, but let's just, get into our testing by opening NetBeans. All is good. Last time we talked about specifications for our functions, why we need testing, and how to figure out if our methods actually work with unit tests. This time we are going even further. What if we could test these methods, our add, our cardinality, all of that, in relation to one another? Like, we could test if isEmpty and cardinality work together, and that if the tree is empty, then the cardinality must be 0, and vice versa. If not, then, something's wrong with our program and we need to look at our code and fix it. This is much stronger than just unit testing. It's testing if our functions work in relation with one another, and if we decide to change one of our functions, we'll know if the changed function has any side effects and disrupts any other parts of our program from the relationship tests type of things. So let's try making something. Going back to, say, our non-empty BST, we'll scroll down to our add method again. What if we test add, member, and cardinality together in a single method, a single test? In our test, we'll add one item to the tree, and the cardinality should increase by 1 unless the item was already in the tree. If the item wasn't a member of the tree already and the cardinality didn't increase by 1, then we have a problem and something isn't right with our methods. And so instead of talking about it, let's just create this method. So we'll go back to our testers and we are going to create one test that checks all of these methods. And because it's in relationship with one another, you're going to be able to see like the whole concept of the program in the test. And so you'll see this in a second. So we'll go public, static, void, and we'll just check, what are we checking? Add, we're checking member, and we're checking cardinality. And so we'll say, there it is. And we'll input a tree like we did last time. We'll throw some methods on it and see if it still works. And throws exception, because we are also going to be doing the same thing that we did before. If something's wrong, we're going to throw an exception. And so we don't have to constantly be looking at print statements to see if something's right. Like we could, instead of how we have here, if T is not empty, but it is an empty BST, then we throw an exception if something's wrong. We could instead do a print statement here saying system.out.println something's wrong, and then otherwise system.out.println nothing's wrong, like it's all good. But that would make us have to look at the print statements and see like, oh, okay, this method worked, this method didn't work. By only throwing an exception when something goes wrong, it allows us not to worry about the console unless something goes wrong. This is super, important to note, and it makes it easier on you when you're testing your code. You don't have to constantly be looking at print statements. Throwing exceptions, it's a lot easier, and it makes more sense because you want your program to error if something's wrong. It's scarier when your program doesn't error and you know something's wrong, but you can't figure out what it is. That's why we need these tests. We need to be able to pinpoint exactly, okay, if we have two methods, like say I was also testing like isEmpty in here, and I was that's not, okay, words. Say I was testing isEmpty in here and isEmpty in here, and I had a bunch of other tests, and these two tests, this one and this one, were the only ones that were erroring, I would know that something's wrong with isEmpty. So we could test all of our methods in a circulation with one another. Does that make sense? So if I go back to my non-empty BST here, we could test like isEmpty with cardinality, cardinality with member, member with add, and then add with isEmpty. And if we had tests like a single test for isEmpty and cardinality together, a test for cardinality and member together, testing their functionality in relation to one another, then if one of these methods isn't right, then say add isn't correct, then member and add, that test, and add and isEmpty, those would be the ones that we're messing up. And it doesn't have to be exactly in this like circular order, but it has to be something close to it so that it's easier to see, okay, this is the one going wrong, versus a unit test where, yeah, you could fix that one test, but it might mess up something else down the road because you added a side effect or something. Just something to think about. I've been talking a lot. Cardinality, there we go. In this method, we're going to have a tree T, and then we're also going to have an int X. And so basically here, we're assuming that everything that we're going to add is going to be an int. And yes, our trees are generic, we made it so. And we could make it so you could add like an element E, but that would take a lot more time, and we want to just get to how do we do testing versus all of the intricacies of generics and how to make that work. But of course you can do that on your own. So we're going to say we're always going to be dealing with integer trees, if that makes sense. So the first thing that we're going to do in this method is we are going to have an int nt, and this is going to be the cardinality of the new tree once we add the element x. And so if we do t dot add x, and then we take the cardinality of this whole thing, dot cardinality. And so we're going to add x to t, and that will return a new tree with everything that t has plus the element x. And then we're going to take the cardinality of that. Because our methods are non-destructive, meaning they do not change their, they're not mutable, meaning they do not change the original input, the original tree. They output a new tree without changing the original tree. That's why we can do this and we won't have problems inside of here. This will return a completely new tree and not change our original t. And then when we get the cardinality of it, we get our int. And so there are basically two cases here. Either something was added and the cardinality increased by 1, or the thing that was added was already there and therefore not really added, so the cardinality stayed the same. And so if the thing that was added was already there, that means it was a member, hence we're testing member. It was a member of the original tree and therefore the cardinality stayed the same. So how do we test this? We have these two cases, 1 and 2. And for the first case, we'll go if nt, meaning the cardinality of the new tree with the thing added, equals t.cardinality plus 1. Then that means the thing was added and x should not be a part of the original tree. So we'll say here, if t dot member e, x actually, is not a member of the tree, then all is good. But if it is a member of tree, then we have an error, and so we'll throw new exception. The cardinality increased by 1, but the thing that was added was already a member of the tree. And so what's going on here? So we'll test if the new cardinality equals the cardinality of the original tree plus 1, then something was added, something new was put into the tree. So say our tree only contains 5, then x must have been 4 or 3 or a different number. So say we have this one tree 5, we add 4 to it, then the cardinality of the original tree was 1, now the cardinality of the tree is 2 once we add another number to it. So then 2 equals 2, and that new thing we added must have not been a member of the tree, if it all worked correctly. But say like 5 is in the tree and then I add 5 again, then the cardinality should be the same. It should still be, one thing, because only one thing is in the tree. And so say the thing that we added is already in the tree, but the cardinality still increased, then we have a problem and we want to throw an exception. Otherwise, everything is good and we're good to go. Else, if nt equals t.cardinality, meaning the cardinality did not change, that infers the thing was not added to the tree because it was already there. So if we add these comments, this is kind of sloppy, but there it is. Okay, so the other case is that the thing that was added was already there, and therefore it wasn't really added to the tree, so the cardinality stayed the same. Therefore, if t.member x, meaning if the thing that we added was not a member of the tree, then the cardinality should have gone up. So we'll go throw new exception. The cardinality didn't increase by 1, but we added a new thing. Otherwise, if none of these two things are true, throw new exception. We'll say just something is wrong with our program, because we don't really know what's going on, because either it increases by 1 or it doesn't increase at all, depending on if X was already a member of, this tree T. But if something like is removed for some reason, if we call member or if we call cardinality or something's happening like that's not right and add, if something goes wrong, then we have just something's wrong with our program, and we'll know to come and check out this method because maybe our test is wrong. Maybe our test isn't testing the correct thing. So let's check this out. Let's go back to our tester. Nope. Let's go back to our binary tree, and we have a bunch of these things, and we can leave these guys here if we want. It doesn't really matter. And we'll go testers dot check add member cardinality, and we'll check E. We'll add 5, and E was our empty tree, remember? So we'll add the empty thing to 5, and then we will go to N, and we will add 5, and it shouldn't add it to the tree. And then because, in our tree, our binary search tree that was non-empty N, it already has 5. So if we add 5, its cardinality should still be 1 because we're adding the same thing again. And then we'll add 6 to this. And so then N would have 5 and 6 in its tree. And so its cardinality should go up by 1. So we'll save, we'll play, and we should get nothing in our console. This is good because that means everything worked out and no errors were thrown. But if you're curious to see which test cases were actually tested, you could go to testers and you could say else all is good, and we could print this out to the console. All is good, our cardinality increased, and the thing wasn't in the tree. And we could say else here, system.out.println, all is good, the thing was in the tree already, and our cardinality didn't increase. Okay. So I'm just going to do this to prove a point, but I'm going to delete it and or comment it out in a couple seconds. So if we play now, here, if we go back to our binary search tree, we had our first test here that's going to print something out is our empty tree with 5. And so if we add 5 to our empty tree, our cardinality should increase by 1. So all is good, our cardinality increased and the thing wasn't in the tree, which is right because we started with an empty tree and we added 5. Okay, next method, N and 5. So our N tree already had 5 in it, and then we're adding 5 again. So all is good, 5 was already in the tree, and so our cardinality did not increase. Makes sense, all is good. Now we're adding 6 to our N tree, so it already has 5. All is good, our cardinality increased because we're adding the 6, which is a new element, and 6 wasn't in the tree originally. So print statements are what you could use to see, okay, are the test cases that I'm thinking are running correctly? Are they, being hit, automatically? And so that's good in the very beginning, but again, when you're doing large test cases, when you're testing lots and lots of things, you'll see why that's not going to work out. We won't delete it yet because I want to prove that point to you, but yeah, so we'll just save that. So something important to remember is that testing is like writing our code twice. We write our code once to test it, per usual, but we use tests to test our code from a different angle. Using instance of in our isEmpty up here, that was another way of attacking this type of problem. We write algorithms to solve problems. This was another way of looking at the problem is empty. How do we show something is empty? Well, it is an instance of empty BST, or the method is empty returns true if it is empty. So let's forget about this for a second and let's just think about this in life and math. And so consider this. If we have x plus x times 2 equals x times 2 plus x. This is a thing, or really you could just do this to make it a little bit similar. So we have x plus x times 2 and then x plus x times 2. These two things we know are equal because of order of operations. We always do multiplication before addition. But this would be a kind of test you could run. Say you wrote this part with your code, and then you can use a test to test if it's equal to this thing, which you know in your mind these two things should be equal. And if they're not equal, then something's wrong with the code you wrote that produces this thing over here. Does that make sense? This is like super crucial. This is testing. Seeing that we get the correct answer, even if we approach it another way, that is what we're doing here. That's what we did with isEmpty in our instance of empty BST. Now, you should always be asking yourself, is this the best way to test our program? Well, we are hard coding our test cases inside of blah blah here. We are actually, like, N and E are hard coded. And that's fine, you know, but what about all the different cases we don't even know about? What about, you know, the test case with 45, 36, 28, all of those numbers in the tree? We haven't tested that. What if we could randomize the input to our test cases to ensure that we were hitting every possible test case? Well, we can do that. We can make random binary search trees. Now, our trees are generic, so we could make, you know, random int generators, random Boolean generators. We can have anything that's comparable inside of our, you know, binary search tree. Booleans are not comparable, but you could create a Boolean class and make them comparable. That's a whole other story. But like you could have, you know, a string generator, a character generator, stuff like that, things that are comparable, and you could make these random binary search trees. For this tutorial, I'm going to assume our input is going to be ints, and so we're going to create a function that creates random binary search tree with ints, integers in them. So we're going to do this inside of our testers class here. So let's save this up, and we'll put this at the top. And we're going to create two methods. One method is going to give us random integers, and another one is going to give us random binary search trees, because what is a binary search tree? Well, you create one by constantly adding numbers. That's how you can create a tree. And we already know how to add because we have the add method in, you know, our tree thing here. So we can add to any tree. And so all we need to do is create a method that produces random integers, and then slowly, or not slowly because we're computers, but and then constantly add them to the binary search tree, and then voila, you have a random binary search tree. All it is made up of random numbers. And so let's start off with our random int class. And this is going to be similar to what you've seen before. I'm going to do it a little bit differently so that you can have a more open perspective of how to create random stuff. So yeah, so we'll do public static int random ints. There we go, and this is going to take an int min and an int max, and so we're going to allow those two things to be, you know, whatever we want them to be, allowing more options for our program. Like, it doesn't just have to go from 0 to 100 or whatever it is. And in this method, we are going to create a new random, rand equals new random, you know, what we always do, and then we're just going to return our random.next int, and we need to import random. And inside of this next int method, we are going to do max minus min plus 1, and then plus min plus min. There we go. This is another way of doing random. And so this looks, I know, really scary at first. It's another way of doing random without the modulo operator. If you just wanted to use addition and logic, this would be a way to do it. You could also use the modulo. And so what this does is we say our max is 15 and our minimum is 5. And so we want it to go from 5 to 15. So 15 minus 5, if we can go down here a little bit, okay. So we'd have like 15 minus 5, that would equal 10. And then you'd have 10 plus 1 equals 11. And so what would this do? This would allow this function to go from 0 to 10, because remember, this is not inclusive. And so our random next int is going to go from 0 to 10. But our min is 5. And so we set our min, if we do, our min equals 5 and our max equals 15. So right now, this whole thing is going to return a random number from 0 to 10. But because our min is 5, we are going to want to add 5 to this random number. And so whatever this, you know, thing generates, whether it's, you know, 9, you know, 10, 2, we're going to add 5 to it, and it's always going to be greater than 5 because we're literally adding 5 to it, and it goes from 0, you know, on. Does this make sense? This takes a while to wrap your mind around. And so say the random number we get is 2, we'll go 2 plus 5 is 7, and we'll return 7, and that's between 5 and 15. Say we get 10, we'll get 10 plus 5, 15, that's between 5 and 15. And you could also get, and this is inclusive, and so our int min and our int max are inclusive, so you could get 5 or 15 or anything in between them. Okay, so now let's make our random binary search trees. And so we'll go public static tree, because we might want to return an empty binary search tree, and we'll go random tree int count, and we'll open and close these curly brackets. And basically, this count is going to tell us how big do we want our binary search tree to be. Do we want it to be, have 10 random integers, 10, stuff, or 5 or 0? What do we want it to be? Well, if our count is equal to 0, then we want it to be an empty binary search tree. So then we're going to want to do return new empty BST, because we don't want anything in our tree. Otherwise, we want to continuously add random integers until our count is at 0. So we'll do return random tree count -1, because we're going to add the element right now. And then we'll do dot add. And what are we going to add? Well, we're going to add a random integer. So we'll just do random int. In here, we'll just hard code this number. You could randomize it, but we'll just go 0 to 50. So everything in our tree is going to be between 0 and 50 inclusive. And so what are we doing here? Well, if we have our count, say it's 5, we're going to add 5 things to the tree using this recursive method. And then once our 5 gets to 0, we're going to return a new empty BST. This takes a while to wrap your head around, but I promise you'll get it. This is recursion at its best. This is how you're going to be using it in real programs. Important to realize. Now let's test this. Let's go to our main and let's mess with this code. So if we go to our binary search tree here, blah, blah, blah. So we have these things. We'll go for int I, and we'll create an integer here that's like tests, the number of tests, and we'll run 1,000 tests. And so for int I equals 0, so we'll start off at 0, we'll go I plus plus, and I will go from I0 to the number of tests that we say there are. And inside of this for loop, we are going to run this function. And so we are going to actually run our tests, our check add member cardinality, and our check is empty. We're going to run these tests inside of this for loop, and we're going to run 1,000 of these. And each time we run a test, it's going to be on a random binary search tree. And so we'll declare a tree T, there it is, and we'll say if I modulo 10 equals 0, so that basically that means like every 10th, I. So when I is 0, when I is 10, when I is 12, when I is 20, whenever the modulo is 0, so it's like every 10th, I, we are going to let our tree equal a testers dot random tree with count 0. And all this is going to return is a random empty BST, but this kind of makes it a little bit more parallel for the thing in a minute. So otherwise our T is going to be a testers dot random tree, and the count is going to be 10. So we are just going to say all of our trees are going to be 10 in length. And you could randomize 10. You could make it equal to I or something. Yeah, that's up to you. And so what we are going to do is inside of this for loop still, we are going to run our check add member cardinality method on T. So we'll go testers.check add member cardinality on T, which could be empty. It could be not empty. And what are we going to add to it? I. Why not? Why not I? And so there we go. We're going to add I, which could be 0, could be 5, whatever iteration it's on. And there we go. So if we press play, we have all of these print statements. Oh my God. And notice you can see, I guess, the frequency of each test case, because we still have, if we go back to testers, we still have these print statements if it works. Like otherwise it worked, otherwise it worked. And yes, we would have gotten an exception if something went wrong, but what if those exceptions that we had here, what if we changed these into print statements? Then we would be searching through all of this to make sure everything is right. And we don't really need these print statements if we know the exception is going to be thrown if something goes wrong. So why would we need them? Well, you could look at to see like, okay, the frequency of each case, the thing was already in our tree. It doesn't happen very often. And because we limited like the stuff that goes in our tree from 0 to 50 with our random ints, later on, it's not going to be in the tree because we're adding I to a tree, which could be like 100, to a tree which only has stuff in it from 0 to 50. But, you can see when different cases were run and stuff. But right now, we don't need them anymore because we know that This second case isn't run as often as the first case, but it's still run, so we still need it. So I'm going to take away, or rather, I'm going to comment out these else's so we don't deal with it again, and we can show that we're going to have a clean console and no errors are going to be thrown because our thing works correctly. So if we comment this stuff out, we'll play it again. No print statements, yay, and it's much cleaner. So wrap your head around this for a second. We just ran 1,000 test cases in like 2 seconds. We could change this to 10,000 to 1,000,000, whatever, how many ever test cases we wanted to run, and we could see if something ever goes wrong. Now, we coded our program first, our binary search tree first, and then we created the tests. Like, we made our non-empty BST, we implemented all these methods before creating our tests. But there is actually another way you can do code where you write the tests first, like you write, if we go to our testers here, you write check add member cardinality and you write check is empty first, and then you go write the code to make the test pass like it's supposed to. This is called test-driven development. In test-driven development, you come up with the test that defines what you want the function to do, and then you write the code that makes your function pass the test. Once your function passes the test, you make the test case harder in a way, so then you have to go and rewrite the code so it works for the harder test case. Now you keep doing this in a repetitive cycle where you change the test, you update the code to make the test pass, you test the case, you change the test again, you write the code that, will make the test pass again, you go back and forth in that, and it's this repetitive cycle until you're happy with your method's, functionality. Basically, in test-driven development, you are making these unit tests for each of your methods for each unit of your program. So you'll make, your check is empty, your check add, all of that. And this is used fairly often in the tech industry and is super important to realize and understand. And so just to review, we talked about what testing means, specifications, unit tests, how to test your functions in relationship with one another, how to make randomized tests, randomized, binary search trees, and test-driven developments. And so that's it for this video. The HackerRank challenge is down below in the description, and if you have any questions, feel free to leave a comment on this video. I hope you learned something, and I will see you tomorrow.